Today we're going to learn about Le Chatelier's principle. It's an important principle that we'll use throughout our unit on chemical equilibrium, and we'll see it pop up back up in different places. So today what we're going to do is learn about it more from a qualitative point of view, and then when we get into some problem solving in our next lesson, we'll see how it's put into practice with quantitative applications. So first we have to learn, well, what is Le Chatelier's principle? Last lesson we learned about what equilibrium means and what happens when a system's already at equilibrium. But now we're going to look at what happens when you try and stress the equilibrium system or change a condition when something's already at equilibrium. So Le Chatelier's principle said, when stress is applied to a system at equilibrium, the system will readjust in order to relieve or offset that stress. Now, what does stress mean? It's any kind of factor that upsets the balance for the rates of the reaction in both the forward and the reverse reactions. So basically anything that's going to change the rate of a reaction is considered a stress. So what are some things we can think of? Change in concentration. You could also say pH. You could say change in pressure. We know a catalyst can also affect the rate of a reaction. So we're going to learn about some of those different things today and what happens to the equilibrium. The equilibrium wants to be reestablished. So if you have a chemical reaction that's at equilibrium and you change one of these things, change concentration, pressure, add a catalyst, etc., the equilibrium is going to want to reestablish itself. Maybe it might look the same, maybe it might look different, but that'll depend on the actual factor that you have. So let's take a look at some of these examples. And the first one's probably the most common one that we will see as we go through our problems and problem solving for the rest of the unit. What happens if you change the concentration of one of the chemical species in your reaction? What if you change the amount of a reactant or the amount of a product? What happens is the equilibrium is going to shift. And when we say shift, it means it's going to move to the right towards the products or to the left towards the reactants. So it's going to shift away from whatever is added. Sometimes it's an ion or compound or whatever that is. So to make it a little bit easier to understand, let's look at an example. So when hydrogen is added to a mixture of hydrogen iodide that's already in equilibrium with hydrogen iodide. So here's our reaction. We see that equilibrium arrow to know that this is a reversible reaction. And what we're saying is here, we're going to add more hydrogen. So what's going to happen here? Well, we said the equilibrium is going to shift away from the added ion or compound. So more hydrogen, it's going to shift away from that, which means it's going to shift in the forward direction. Another way of saying this is you could say it's going to shift to the right, because that's the actual direction. Or you could say it's going to shift towards the products. Any one of those descriptors would work for describing what happens when you add more equilibrium. And so what's going to happen, it's going to push the equilibrium immediately to the right, but then it's going to try and reestablish equilibrium. So after that initial shift that we've recorded down here, it goes back and forth and back and forth until that equilibrium has been reestablished. So kind of like a back and forth pull, and every time it goes back and forth, it slows down until that equilibrium has been reestablished. So let's try a different scenario now. What if we remove some iodine. So what if we have less iodine? If this happens, then the equilibrium does the opposite. Instead of shifting away, it's going to shift towards the atom or ion or compound that's been removed. So if we have less iodine, the equilibrium is going to want to replace it. How is it going to do that? It's going to push the equilibrium in the reverse direction so that some of this hydrogen iodide, that's the product, is going to break down and produce some of the iodine to replace it. So here, if we use the same kind of description, we can say this one's going to shift backwards. You could also say it's going to shift to the left, or you could also say it's going to shift towards the reactants. You don't need all of these, just any one of these would work for your description. Okay, let's try out one more now, and I'm going to let you try this one here. So what if I took away some hydrogen iodide? What if we have less of this? Take a minute and think about which direction is the equilibrium going to shift. Here, since we have less hydrogen iodide, the equilibrium's not happy. It's going to want to replace some of this. If we remove it, the only way to replace it is to react our hydrogen and iodide to make more hydrogen iodide. So here, we're going to have a shift forwards. Or you could say again to the right, or towards your products. So how's an easy way to figure this out? If you're familiar with a seesaw basically provides a good analogy to figure out what these changes are going to do. Which way is it going to shift? So let's walk through a couple of scenarios together. So if you're on a seesaw and you are perfectly balanced, your friend that's sitting on the other side of the seesaw is perfectly weighted with you, and the seesaw is completely parallel to the ground, you could say their reaction is perfectly at equilibrium. But what if we disrupt this equilibrium? So let's take our seesaw and let's say that we add more mass to the left-hand side. That's going to disrupt the equilibrium. It's not balanced anymore. So which way would you have to shift your seesaw to get it to go being back at equilibrium or being parallel to the ground? It's going to have to shift to the right or forwards. So you have to move some of that weight from the left-hand side to the right-hand side. And we want it to go back to being equal on both sides. You can do this with your pencil too. You can hold your pencil up in front. If you weight it down on one side, if you want it to go back to equilibrium, it's got to shift forward or shift to the right. Let's look at it just from another example. So what if you had the opposite? What if we have more on the right-hand side because we've taken away something that's been on the left-hand side or our reactant side? This time, it has to shift backwards. That redistribution of weight has to go backwards if we want that seesaw to go back to being parallel to the ground. So this is a cute little trick you can try, really good with your pencil, holding it up and down, trying to see, well, which way is it going to go? If I add some mass, if I take away some mass, what's going to happen? So now we'll look at another stress on the system, and this one's a little bit different. What happens when you change the volume or the pressure? So think back to some of your knowledge on ideal gas laws from grade 11. If we decrease the volume, we see an increase in pressure. Or if we increase the volume, we see a decrease in pressure. They are oppositely related. So if you remember P1 V1 is equal to P2 V2, that's where that pressure and volume relationship come back. Don't worry, we're not going to do any calculations with that here, but just something to keep in mind. They're oppositely related. So let's look at an example to see what's going on, and hopefully that'll help understand a little bit more about the result. So what happens when the pressure on the system is increased in this case? Pressure increased means our volume has gone down. There's less room here for this reaction to take place. How we do that is figure out first how many molecules we have on both the reactant and product side. So on the reactant side, we have 4 molecules. And on the product side, we have 2 molecules. How do we know that? 1 molecule of nitrogen plus 3 molecules of hydrogen. 1 plus 3 is 4. On the product side, it's a lot easier because there's only 2 molecules of the same compound, that ammonia gas. So when we're trying to figure out in this scenario what happens when the pressure is increased, what happens is the system will shift towards the side with fewer number of molecules. So if your pressure increases when the volume decreases, the equilibrium shifts to the side with fewer molecules. So if we look at this example up here, which side has fewer molecules? The reactant side or the product side? Here you can see the product side has the fewest number of molecules. So therefore the shift is going to occur to the right or forward. If we had the opposite case, the opposite is true. If your pressure decreases, or you could say the volume increases, the equilibrium is going to shift to the side with more molecules. So this is going to depend on your example and your chemical reaction, but always count. Look at which one has the most number of molecules or the fewest, and then decide what happens if the pressure increases or decreases. Next up, we're going to look at temperature. So this is an important stress. What happens if you change the temperature? Now this is where a little bit of your knowledge on thermochemical equations can come in handy. So if you remember from Unit 2, when we look at our thermochemical equations, there's 2 ways you can represent it. One is with enthalpy, or the energy written separately. Delta H is equal to positive or negative and whatever the value is. But what I would do is strongly, strongly, strongly recommend that you use this format for thermochemical equations. Write your reactants, write your products, and include the enthalpy in the equation. Why do we do that? It helps you figure out which direction is going to be shifted a lot easier. You can pretty much treat it like an example that we saw previously with change in concentration. It's a little bit different, but the shifts work the same way. So let's take a look at this example. What would happen when the temperature of the system increases? So we'll look at that one first. An increase in temperature means you have more energy. More energy means you're going to have more energy over here. And if we treat this like it's part of our equation, we've got more added to the right-hand side. And we said before the equilibrium is going to shift to oppose that addition of more compound, but now it's more energy. So it's going to shift away from it. And it's going to cause that shift to move to the left or push it in the backwards direction. So here, it's going to shift in reverse or to the left. Okay, but the other way you could look at it is which direction is it's going to shift in terms of endothermic and exothermic. We can see that this reaction has energy on the product side or a negative enthalpy, so we know it's exothermic. But if it's going to shift in reverse, that means it's going to shift in the endothermic direction. All right, let's try what happens in the opposite case. What would happen if the temperature decreased? If the temperature decreased, that means we have less energy on this side. The equilibrium doesn't like this stress. It wants to replace some of the lost energy. So it's going to do the opposite. It's going to shift towards the amount that has been removed. So when this happens, here we're going to see a shift forward in this example. Forward towards the products, or you could say to the right, but this means it's going to shift in the in the exothermic direction. This will vary forward or reverse depending on whether you start with an endothermic reaction or start with exothermic. But if you make sure that you always write your equation with energy on the reactant or product side for endothermic or exothermic, it makes it work very similar to your concentration situation. You can also look at it from a point of view of the seesaw. If we want to go back to that model for both of them, if we had our scenario where the temperature was increased, before the temperature was increased, we had a balanced seesaw. Here, if we increase the temperature, we said that we're adding more energy on the product side. So all of a sudden, our seesaw is going to look something like this. We said more over here. And how is it going to return back to equilibrium? Well, it's going to have to shift backwards or shift in reverse to get that parallel balance to the ground that's there. Let's look at a few more conditions where we'll see stress on an equilibrium. The other two aren't as common, but you'll run into them into some practice problems, so let's make sure that we go over those. What happens when you have a catalyst? So remember what a catalyst does. A catalyst is going to decrease the activation energy for a particular reaction. So what that means is it's going to cause the reaction to occur quicker in less time. If it's with equilibrium, it just means that reaction is going to reach equilibrium in a shorter period of time. So if we add a catalyst, it actually affects both directions at the same time. The forward and reverse are affected to the same extent. The forward rate increases and the reverse rate increases. So when you look at the equilibrium, it doesn't really look like there's been a shift that's taken place because both directions have been affected. The last scenario is what happens when you add an inert gas. So if you add an inert gas to a system, sometimes it's there just to help with the pressure or provide a certain atmosphere for the reaction to take place. So sometimes oxygen is not favorable because things react in oxygen, so you use a different gas instead. Using these noble gases is one thing that's sometimes done. So we know all of our noble gases. So if these are added, it might change the pressure slightly, but here there's actually no effect because the number of successful collisions don't change. And if the number of successful collisions don't change, then the rate of the reaction doesn't change. So if you have a noble gas being added, you won't see any shift happening with your equilibrium or any change. So what I'm going to do next, here's a problem for you to try out. There's several different conditions that you should try out. There's A all the way to E. So I'm going to pause the video now and give you a couple of minutes to try and make sure that you try this example with the different shifts that could happen. And then let's regroup and go through the answers together. All right, so we're back. Hopefully you've had a moment to try this problem out. So first thing that we would always want to do is take our energy and put it into the equation. Here we've got a positive enthalpy, so that means this is endothermic. Endothermic, our energy is going to be on our reactant side. So I'm going to put that in there, and I'm going to use this equation here with the energy written in there to follow along with my answers. So what happens here? What if I remove some PCl5? PCl5 is a reactant. If we use our analogy of the seesaw, we have less on our reactant side. So here my seesaw looks like this. If I want it to return to be balanced or parallel to the ground, I know that my equilibrium has to shift backwards. It's got to push that seesaw down so that it gets parallel back. So here I know my equilibrium is going to shift in reverse or to the left. Let's look at the next example. What happens when we add some chlorine? Chlorine over here is a product. So think about your seesaw. If we add more to the right-hand side, it's going to make it heavier. Looks similar to the previous one now that we've drawn out our seesaw, but it's a different reason. So what's going to happen? We have to redistribute some of that mass from the chlorine to the other side. And what's going to happen? That equilibrium is going to shift to the left or shift reverse. Okay, next up, what happens? Let's put this all on this page here. What happens when you increase the temperature? So if we have an increase in temperature, let's go back up here for a minute. More energy is on the left-hand side. That means on your seesaw, it's going to be heavier on the left-hand side. So if we have that here for our seesaw, more energy on the left-hand side, it's going to be pushing down like this. It's got to move to the right to balance that seesaw back, which means here it's going to shift forward. Now, if we wanted to make this more specific, is the forward direction endothermic or exothermic? Well, we identified that here as being endothermic. So we can also say endothermic direction. Then there were two other parts, part D and part E. I'll write them up in here so we can follow along with our example. D said we're going to add some HE. Now HE, if you remember, is a noble gas. Anytime we add a noble gas, here there's going to be no change in equilibrium or no shift. It's not going to change the reaction itself, so we're going to notice no shift. And then E, if you try this one out, it was using a catalyst. Again, what happens with a catalyst? it's going to speed the rate of the reaction up in both directions equally. So forward and reverse are both going to speed up. That means, again, you're going to notice no shift overall. You could also say both directions speed up, but because they're balanced out, you won't notice the shift. So hopefully that gives you a good idea about the Chateliers principle, but this topic does require a bit of practice. So make sure you try out all the suggested practice problems and also take a look at the JFR science video because that'll also give you another perspective on all of the different components with Le Chatelier's principle.